Alright, let's do a crazy problem that combines buoyancy and thermal expansion. I don't know. So I'm going to say we have a mass. When it's fully submerged underwater, we know its force of buoyancy. So the force of buoyancy is, we'll say it's, I don't know, 10 newtons or something like that. Okay? And that is when its temperature is at 20 degrees Celsius. Now let's say that we increase the temperature of this thing to, well, let's say we increase it by like 200 degrees, and now it's 220 degrees Celsius, and the new force of buoyancy is 10.1 newtons, like that. Okay, so it's not increasing by much, but there it is. So let's find what the volumetric coefficient of expansion for this thing is, beta. Alright, so the volumetric coefficient of thermal expansion. First of all, let's see, why would the force of buoyancy increase? Well, let's think about it. If we increase the temperature, that means we increase the volume. And if we increase the volume and are still submerged, that means we're going to have more buoyant force. Okay, so let me call this force of buoyancy 1. And that is temperature 1, force buoyancy 2, temperature 2. So I know that the force of buoyancy 1 is equal to density of the fluid, volume of the fluid displaced, which is in this case the volume of the object, volume 1, times the acceleration of gravity, and force of buoyancy 2 is the density of the liquid times the volume of the liquid displaced, which is different now, right? Because it's going to change in volume when we change the temperature, times g, like that. Okay, now we're looking for beta, so I should probably write this equation down. We know that the change in volume is equal to the initial volume times the volumetric coefficient of thermal expansion times the change in temperature. Okay. So I have final and initial volumes, right? Let me actually rewrite this in a way that makes more sense for this equation. We know that the, so delta V would be V final V2 minus V1 equals the initial volume is actually V1, right? In this case, the way that I've chosen my variables. There's that, right? Now I'm looking for beta, yes? So we can go ahead and solve this thing for beta. Beta equals V2 minus V1 over V1 delta T. Only problem is we don't know the volumes. But, well, what if I rearrange my buoyancy force equation? I could just solve it for volume. Oops, did that one wrong. There we go. Alright, so having done that, we can plug these definitions of volume in. Get beta equals force of buoyancy, oops. I'm just going to say force 2 because I'm lazy here. So the force 2 over rho g. Volume is force of buoyancy 1 over rho g divided by volume 1 is force of buoyancy 1 over rho g times the change in temperature. Well, we don't know the density of the fluid. I don't think I mentioned it. So luckily, we have a 1 over rho g everywhere, and we can cancel it out, right? It divides out like that. And so beta ends up equaling F2 minus F buoyancy 1 over F of buoyancy 1 times the change in temperature. And so that is our volumetric coefficient of thermal expansion. God, that's a long name for these things. There it is, whatever it's called.